All right, in the last video what we did is we talked a little bit about this concept of electric flux and sort of its relationship to the electric field and the area vectors that are associated with the surface that you draw. In this case, what we're going to do is we're going to talk a little bit about curved surfaces, so we're going to stick with a point charge, and we're going to continue to sort of build this idea of what is the electric flux. So what I have drawn here is a point charge that has electric field vectors that point radially away from it everywhere in space. And what I'm going to do is I'm going to sketch over top of it a sphere. So this is a sphere that goes all the way around the charge at the same distance r. So it's sort of, the charge is centered and the invisible surface is a distance r away from it everywhere. So you know that the electric field associated with that charge at any of those points is 1 over 4 pi epsilon naught q over r squared r hat, right? So it points radially outward everywhere. And what we're going to do is we're going to find the total electric flux associated with this situation. And what I mean by that is in the last video what we did was we calculated the electric flux over a surface, but it was an open surface in the sense that it didn't enclose a volume, right? So the total electric flux, when we talk about that, what we mean is that we've created a bubble, something that encapsulates some charges, and so we want to know what the electric flux is over the entire encapsulated space as opposed to just through one side of it, for example. So in this case, what we're going to do is we're going to calculate from scratch the electric field dotted into dA, because that is the definition of the flux. Now what we're going to do is we're going to go over this whole surface. So in fact this is a closed integral, and normally we would put a little circle here to indicate that that's the case. But what we're going to do is we're just going to say we're going to find the total. We're not going to complicate it any more than that. Now with this spherical surface we have dA vectors that point perpendicular to the surface everywhere. So if I draw one really close to this guy, it's perpendicular to the surface, which the electric field vector is also perpendicular to the surface. They both point radially outward. If I look at some other location, that dA vector also points radially outward. If I look over here, that dA vector also points radially outward. So everywhere that we have electric field drawn, the dA vectors, the little dA vectors, point radially outward. So that indicates to us that if we were going to actually do this calculation, the dA vector would essentially be whatever little patch of surface that we care about, which we'll say is just dA magnitude, but it also points in this r hat direction. It points radially outward. This is the kind of thing that we like to see when we're trying to build up this idea of Gauss's law and electric flux, is that the electric field and the dA vectors share the same direction, right? That is really, really helpful, because when we put this into this calculation, what we're going to find is that these two vectors point in the same direction, and it makes this integral much simpler to deal with. So we'll go ahead and do that, right? So the total electric flux is going to be the integral over the whole sphere of 1 over 4 pi epsilon 0 q over r squared. Now the r hats will dot into each other and they'll go away, times dA. That's the integral that we're going to be left with. Now the thing that's really special about this integral is that the distance that we are at is a fixed distance, right? The surface of the sphere is defined by how far we are away. So the electric field is a constant magnitude. So the simplest thing we could do is actually redefine this little r as a fixed capital R. That is the distance that we are at, and that's it. And if that's the case, then we have calculated the total electric field at any given point, due to that point charge, is 1 over 4 pi epsilon naught q over big R squared. Which means that this is a constant. This is a constant over that whole surface. And in fact, we can take that out of the integral altogether. And so what we have is a situation that we really are happy to have, which is that the electric field is constant over that surface, leaving us with an integral over the whole sphere of just the area. So there's two key points here that we had. One is that the electric field and the dA vectors are oriented in the same direction. We like that because it makes this integral really simple. The other thing we like is that the electric field is constant over the surface. constant magnitude. That gives us this result, which essentially just tells us that it's the electric field magnitude multiplied by the surface area of the whole sphere. This goes back to the very first video when we talked about motivating Gauss's law. So in fact, what we have is 1 over 4 pi epsilon 0 q over big R squared. The surface area of that whole sphere is 4 pi big R squared. And so the total flux through that entire surface is a constant, just like we talked about in the very first video. And that constant is a specific constant. It is the total charge that we've enclosed divided by the permittivity of free space, epsilon 0. So this is a really interesting result, which is that for these kinds of situations where you have charges that are fully encapsulated, the total electric flux is actually just directly related to the total charge that you've enclosed. And that only happens because the electric field of a point charge depends on 1 over r squared. So if it didn't depend on that, we'd have a big problem because the flux would depend on exactly how big your surface is. It doesn't depend on that at all. It just depends on the amount of charge that's inside. And so this is a very important result for electrostatics, because what it does for us is it helps us build this idea of Gauss's law, which is a very much simplified way of calculating the electric field in certain kinds of situations.